Back in the day, the early sea explorers brought rabbits with them for food. So they stopped on a particular island, and two rabbits, a male and a female, escaped. And this island was deserted, had no predators, and so the rabbits did what rabbits do and produced offspring. Each pair of rabbits produces 6 offspring, so we can think about each rabbit producing 3 each. So each pair is going to produce 6, and that'll make the math make a little bit more sense. Okay, so each pair produces 6 offspring. So we're going to assume that the rabbits never die and they only reproduce one time. And how many total rabbits will there be after n generations? So what we see here is that we started with the 2 rabbits. They had 6 babies, okay, 3 each. The 6 ended up having 3 each. That's 18. Okay, 18 became 54 on the next generation, and then 162. And then we had 486, and then we had 1,458. That was after 7 generations we had this many rabbits, this many new rabbits, okay? Now, how many rabbits were born on the 20th generation? Well, if you notice, what do we have here? We have a geometric sequence, 2, 6, 18, 54. We generated this by multiplying by 3 each time. So a sub 1 in this case is 2, and r is equal to 3. And so a sub 20, the number of rabbits born in the 20th generation, should be a sub 1 times 3 to the 20 minus 1. And if we do that, we get a pretty gigantic number of rabbits of 2 billion, that's with a B, 324,522,934. That's just how many were born in the 20th generation. Since these rabbits never die, all of the rabbits before them are still alive. So how many total rabbits do we have? Well, we started with 2. We had 6 more, so that gives us 8. Then we had 18 more, that gives us 26. We're going to continue and get 80 total, 242 total after 5 generations, 728 total, 2,186 total at the 7th generation. And now here, how do we add these up to get a total? So you might guess that this is going to be a geometric series, which is going to be a sum from k equals 1 up to n of something, and that something is really this. Okay, it's going to be our a sub 1 times r to the n minus 1. So again, instead of doing this over and over and over again, we're going to see that we're going to get a formula. Okay, nice, easy formula to work with. And it turns out that that formula gives us a total number of rabbits at the 20th generation, including all those that were born before, of 3,486,784,400 rabbits. That's a bunch of rabbits. Now in reality, they would probably run out of land or run out of food, and eventually the population would level off. But the point of this is to show you that we have sequences and series, or sums of the sequences, that go together, and this is a little story, a little scenario that might illustrate that. So let's see how we're going to actually do this calculation here. It turns out that the sum of a geometric sequence rather, which is called a geometric series, okay? A geometric series is the sum of the first n terms of a geometric sequence, and it follows this formula. So here is the sigma notation version. We're going to add up each term of the sequence from k equals 1 to k equals n, and we end up with a formula that, again, is fairly simple. Okay, maybe not quite as simple as the last one we had, but all we have to do is plug numbers into the calculator. So we said that a sub 1 was our initial number of rabbits, r was 3, which is how many offspring each rabbit has, so each pair gave us 6, so each rabbit gives us 3. And if we plug that in here, we get 2 for a sub 1, 1 minus 3 to the 20th. Now be careful we don't subtract 1 here. This is just n. And we divide the whole thing by 1 minus 3. We plug all that in. We get that gigantic number on the previous page, which we're representing here in scientific notation, which isn't a bad idea when numbers get really big. Okay, so I've put the formula back down here just for reference, and really this part right here. So let's go ahead and try a few examples here. So once again, we need the value of n, we need the value of a sub 1, and we need the value of r. So notice in this case r is negative. So the total sum here is going to be equal to a sub 1 times 1 minus negative 6, notice the parentheses, raised to the n power, not n minus 1, divided by 1 minus negative 6. Oops. And when we do all that, we get a grand total of 31. Okay, same procedure here. Going to pick off our numbers. We have a sub 1 in this case now is equal to 2. So we'll have 2 here. We're going to take 1 minus r is 3, raised to the 7th power, divided by 1 minus 3 by itself. And that gives us a total of 2,186. Now you might remember this number from our rabbit example. This is the total number of rabbits, including those that were already born, previous generations. This is the total number of rabbits after 7 generations. Okay, and the last example here has some interesting results, and again, this is going to play into what we're going to do on the next lesson here. So let's just take a look at what happens when we have a number whose magnitude is less than 1 here. We're going to follow the same formula. We're going to have negative 4. We're going to have 1 minus 1/3 to the 23rd power divided by 1 minus 1/3. 1/3. Thank you very much. And if we do that on the calculator, this tells us that we have negative 6. Now that's interesting for a couple reasons. One, because you see that these numbers are growing very quickly with fairly small numbers for n. In this case, we've got a pretty large number for n, but the number is actually at negative 6. And in fact, I would say you should sit down right now, pause the video, and run this again with n equals 100. Pick a big number here. And you're going to end up getting the same number, negative 6. Now, why is that true? The reason it's true is because every time we multiply our number in the sequence, or term in the sequence, by 1/3 to get the next number, we get a smaller number. And so we start off with some number, the next number we add to it is 1/3 of the size, the next number is 1/3 of that one, the following number 1/3 of that one, and so forth. And the number keeps growing, but you notice it's growing much, much, much more slowly. And it turns out that even if we add an infinite number of terms, it's going to level off at some number. In this case, it levels off at negative 6. So to find this sum up to the 23rd term, we actually have negative 6 and probably some decimal places after it. But we're really, really close to negative 6. So these are a little bit difficult here because of that they're actually converging onto a number, and we may not have enough digits on our calculator to take care of that.